In this section, we'll discuss two types of tolerances, runout and profile. Runout. It's recommended for surfaces of revolution relative to a common axis. It indicates the maximum indicator range when the part is rotated 360 degrees. There are two types of control, circular runout and total runout. Tolerance zone for runout. Notice the runout is referenced to the datum D, which implies that it is the referent axis. The tolerance zone is formed by two concentric circles located in this datum. The tolerance zone is bidimensional. One way to inspect the runout is holding the part from the datum feature, then making it rotate 360 degrees and observe the total range of the indicator. It should not exceed the tolerance value. Note that not only the shape of the feature is controlled, but also the location of the axis against the datum. If this is offset, the runout is greater. Total runout is a composite control that affects the form, orientation, and location of all surface elements simultaneously, in diameter or surface, relative to the datum axis. Tolerance zone for total runout. In this case, we have total runout of 0.01 against datum G, which is the axis formed by this feature. The tolerance zone is two coaxial cylinders where the surface must lie. Unlike circular runout, this area is a three-dimensional tolerance. The inspection is also made as a circular runout by rotating the part 360 degrees, holding the datum axis indicated. But in this case, it is made along the entire surface. Runout is applied in mechanical elements that rotates to high speeds to prevent these elements to produce vibrations. Some examples are the wheel hubs, drive shafts, or general shafts. Now let's talk about profile tolerances. A profile tolerance specifies a uniform boundary along the true profile within which the elements of the surface must lie. There are two types of profile control: profile of a line and profile of a surface. Tolerance zone. In this example, we have a profile of a surface tolerance of 15 thousandths against datums D, E, and F. The surface is defined entirely by basic dimensions. That defines the theoretically perfect profile. From this perfect profile, a uniform offset boundary is generated. Profile of a line versus surface. The tolerance zone established by the profile of a line tolerance is bidimensional, extending along the length of the considered feature. The tolerance zone by the profile of a surface tolerance is three-dimensional, extending along the length and width of the considered feature. In the profile tolerances, whether of a line or a surface, you can specify 4 different tolerance zone types. Bilateral tolerance zone, with equal distribution or unequal distribution. Unilateral tolerance zone, to the outside or to the inside. Bilateral zone, equal distribution. The tolerance zone is a uniform boundary centered with the ideal profile, i.e., we have half of the tolerance in each direction. This is the most used distribution, and that's why it's the default one. Bilateral, unequal distribution, is recognized by the phantom lines offset the profile. The tolerance zone is a uniform boundary, but in this case displaced outward 0.05 from the ideal profile, and the rest inwards, as indicated by the basic dimension from the phantom line to the ideal profile. Unilateral outside. The tolerance zone is a uniform boundary of 0.01 in this case, and is fully outwardly of ideal profile. Note the phantom line is located outside the ideal profile, indicating the direction of the tolerance zone. Unilateral inside. The tolerance zone is a uniform boundary distributed entirely into the ideal profile, as indicated by the phantom line. Just as we have different tolerance type zones, we also have different coverage or extents of the tolerance zone. We have by default, between 2 points, and all around. Let's see first by default. The tolerance zone covers the surface to the tangent points of each side. Here we see indicated in this feature, it covers the extent of the straight line up to the tangent points of each side. Between points. The use of the symbol between extends the coverage area of tolerance to all surfaces between points A and B. As we can see here, there are two paths from A to B. The tolerance zone must pass through the indicated surface with the arrowhead. And finally, let's see all-around extent. Note that the all-around symbol is on the break of the arrow line. The tolerance zone covers all the surface around the outline in the view shown. Now let's talk about the datums on this geometric control. When a profile control is specified with reference datums, it controls form, orientation, and location of the shape. When a profile control is specified without reference datum, it controls only form. Now, we'll see the differences when a profile tolerance refers to 3, 2, 1, or no datum. Let's first see here. We have a profile tolerance of 10 thousandths against datums A, B, and C. Notice that the circle in the break of the leader, so the tolerance applies all around. And being against 3 datums, the tolerance zone is fully immobilized. All of the points of the feature with tolerance must be within this area. In this case, it's the same profile control of 10 thousandths all around, but regarding the datums A and B only. The piece is not completely immobilized, and it can be moved as the datum C doesn't stop it, and therefore we have freedom in that direction, to try to make the surface to lie completely inside the tolerance zone. In this other case, the profile is specified only regarding the datum A. So we can move the piece in 2 directions to try to make the surface lie completely inside the tolerance zone. And finally, here we have the profile tolerance without any datum indicated. So it becomes simply a form control. Remember that form controls don't relate to datums. The part can be oriented in any direction to try to make the surface to lie entirely within the tolerance zone. The use of this tolerance is very broad, since it's practically used for all parts with complex surfaces, i.e., they have no flat surfaces or constant radii, as are automotive parts, sunglasses, plastic parts, even in larger parts as the aircraft fuselages or turbine parts. Method of inspection. One way to inspect this tolerance is by using gauges with the shape and size on the borders of tolerance and pass the piece to be inspected to ensure it meets its tolerance. Another method of inspection is through measurement arms that locate points of the part and compare them with the perfect model to see its variation. Conclusions. Runout tolerances are used primarily in rotating elements and are useful to prevent imbalances. Profile tolerances are useful to control complex surfaces.